Blackboard. Things get clear anyways. All right, so let's talk a little bit about generalities that have nothing to do with the class first, or at least not with the mathematical part. So you can find some information at, I guess, is impa.pa.Heluani. There should be a link there already to a Lie algebra class, and there should even be a homework there. So how this is going to work, let's talk about the bad part first. Let's talk about the grading. So 30% of your grading is going to be homework. So this is going to be problem sets. I was also 20 years old. I understand you're in January in Rio. You want to have fun, go to the beach. The homework is going to be quite easy. It's just 10 problems. Some of them, if not most, we'll solve here. You can do it in groups, but it is going to be required, and I'll expect you to produce this homework every Monday. If you want to switch the day of the week, which the homework is due, we can do that, but every week you're going to have to write down some problem sets. Most of them are going to be trivial. The other 70%, let's say, is going to be 35% and 35% on 2 exams. We should set up the dates for these exams probably next week. But I hope that one of them should be from 7 to 11 of February, because I'm not going to be here that week, and the other one by the end of class. Okay, so a couple of more things. It's been 10 years since I was a student, and, well, no, I guess not a grad student. It's been 8 years since I started grad school. 2 hours straight of mathematics is just unheard of. You can't pay attention for 2 hours straight, and I can't give a class for 2 hours straight. So if you don't mind, we'll take a break in about an hour, 15 minutes break, say, and come back. But 2 hours is just too much to pay attention. Another thing is, you may have heard, I could spend the first class giving motivations as to why to study Lie algebras. I'll tell you what we won't do in this class. There's a lot of geometry behind Lie algebra. The study of Lie algebra started from trying to study in Lie groups. Sophus Lie actually was trying to study the local properties of Lie groups. You can motivate them by physics because you want to study symmetries of systems. And then it's easy to introduce Lie groups. There's a deep interplay between Lie algebras and Lie groups. We won't see this. We won't see any geometry whatsoever. I'll try to keep this class as algebraic as possible. I don't want to mention at all the geometric properties of Lie groups. In this way, we'll lose a lot. There's plenty of things that are quite natural from the geometric perspective. But we'll also gain quite a bit. We'll gain in generality. Everything I'll say will be true in characteristic P, for example, or most of the things I'll say. But also because I didn't want to deal with geometry, because I wanted you to as the only requirement, you should know linear algebra. I expect you know linear algebra, but nothing else. So I don't care if you know what a variety is or what a manifold is. But linear algebra, I expect you to know. Okay, so some bibliography. I will be following some lecture notes by Victor Kax. So these are lecture notes that are given at MIT. Every year, Victor has his students write down the lecture notes, so you can probably find lecture notes for the past 10 years. I think the code is, I'm sure you can find them, but The MIT code should be something like 17745, something like this, or 18745. Anyways, if you don't find them, Lazaro has them, I have them, I can send you the link. This is mostly what I'll follow. Anyways, those lecture notes are quite close to Humphrey's. This is introduction to the algebras. And representation theory. And these two things are really similar. This is quite a dense book, and it's purely algebraic as well. Some other book that you might want to take a look is, what's there on the table, is Jacobson. The Algebras. I think there's only one copy in the library, which I have, but I'll return it today. This book has some results that this one doesn't, but this one is much more complete. If you're interested in Lie groups and in the geometric part, then you should take a look at NAPS. Lie groups, beyond an introduction. Which is quite a good book. All right, so should I say anything else before starting? What else do I need to tell you before starting actually the class? Well, if I forget something, I'll come up with something later. All right, so before I forget, the homework is already there, and the first one is due next Monday. I'm not sure if you all will be here during the whole summer, but if you're all during the whole summer, then it's going to be a problem for me to grade all those homeworks. But anyhow, we'll see how we do that. All right, so let's start slowly. I'll try to make this as basic as possible. If at any time I'm going fast, stop me. If I'm going slow, it's your problem. I'm not gonna go faster, but I'll try to go as slow as possible. It's never the case that you go slow enough anyways. Okay, so let's start with the definition. Okay, I should have... An algebra is a vector space say V with a bilinear operation called product. People usually denote that with a dot, and being bilinear means that if you have, say, A times alpha B plus beta C, this is the same thing as, let me write it first and then we'll do it. So here's the dot. Alpha A dot B plus beta A dot C. And the same for linear combinations on this side. Alpha A plus beta B dot C. This is the same thing as alpha A dot C plus beta B dot C. Where here alpha and beta are elements of the ground field. And here A, B, and C are elements of the vector space. So there's no more requirements on what an algebra is. Actually, before giving that definition, I should have mentioned, from now on, I'll denote fields by either a K or an F or sometimes even this K. Depends on how I wake up that day. But unless I say differently, this field can be anything. So, I mean, as examples for these guys, you can have finite fields. You can have the real numbers, the complex numbers, the rational numbers. You can think on weird stuff like QL bar. Or even local guys like FQ and Lorentz series. But anything is fine. And in particular, I'm not assuming that the characteristic is 0. Okay, so an algebra is just something with a bilinear operation, nothing else. But oftentimes you want some more structure. So an algebra is called associative. Associative if the following is true, if A, B times C minus A times BC is equal to 0 for every A, B, and C in the algebra. An algebra is called unital, well, if you have a unit for that product. Well, let's just say it's called unital if there exists one inside of the algebra such that 1 times A is equal to A times 1, which is equal to A for every A in the algebra. And most of the time in the literature, if you're reading an algebra or a field, people refer to associative unital algebras. Since we're going to be dealing with algebras that are non-associative and certainly not unital during most of this class, then we better make the distinction. Finally, an algebra is called, just say it's called commutative or abelian if A dot B minus BA is equal to 0 for every AB in V. Okay, so that's as much for algebras. We will be dealing with something that replaces two of these axioms. So Lie algebra is a different beast. Definition. A Lie algebra well, it's an algebra I usually use this letter G for Lie algebras. But the product, instead of using it denoting it with a dot, the product I'll denote it like this, with the bracket. It's still just a bilinear operation, such that, while two axioms hold, one of them is something that replaces commutativity. It's going to be skew commutativity. So this is the fact that the product of any object with itself, any element with itself, is 0. So that's called skew commutativity. And something that replaces associativity, well, associativity there is an equality. If if you want, whenever you give me an identity for 3 elements in the algebra, well, we're going to have something like this too. So there's plenty of way of writing this. It's called the Jacobi identity. But I'll like this form. It's quite similar to that kind of identity there. All right, so that's a Lie algebra. So it's an algebra. It's a vector space with the bilinear operation satisfying these 2 axioms. And why skew commutativity is called skew commutativity, why this is somehow a replacement for this kind of equation? Well, notice, so I guess a remark, on a Lie algebra, you always have, so if G is a Lie algebra, then the product of A and B is never, here, instead of being with a minus, it's with a plus. The product of B with A is equal to 0. So the only thing I'm changing in the commutativity axiom is this minus becomes a plus. And this is trivial to prove. Just take the product of A plus B with itself. Because of skew commutativity, this guy is 0. And, well, because of bilinearity, this guy is the product of A with A. I should stop calling it product. I'll start saying bracket, but it is a product anyways. Plus the product of B with A, plus the product of A and B, and plus the product of B and B, which again, by these axioms, skew symmetry, skew commutativity, those 2 are 0. So it makes sense to call these guys, to call that axiom skew commutativity. All right. So what are examples of these algebras? Well, the first example is, let's find an example which is commutative. So it makes sense that if I have an algebra such that the product is skew commutative and commutative at the same time, then if I make G with the bracket being 0 for every AB, this satisfies all axioms, and this is called an abelian Lie algebra. So a commutative Lie algebra is just a vector space. And the bracket is 0. The product of any 2 elements is 0. Okay, some non-trivial example, let's see. Another example is, say, I think if you're learning calculus, perhaps, that take R3 to be your vector space over R. And the bracket, say you have one vector in R3, another vector in R3. Define the bracket to be the cross product of the 2 guys. This is clearly skew commutative. The cross product of 2 vectors that are parallel is 0, so this axiom is obvious. But Jacobi is non-trivial. Check it. It's non-trivial. But that's a Lie algebra, and it's non-abelian. Certainly, there are 2. If you take 2 nonlinear independent vectors in R3, their bracket is non-zero. So this is not an abelian Lie algebra. So let's see. While I defined you some objects, because typically in mathematics, if you define any kind of algebraic object, you want to know what their morphisms are. So actually, Lie algebras form a category. So a morphism. Oops. Lie algebras. Say from G1, say G1 into G2. The morphism F from G1 into G2 is a linear map so F is a linear map of vector spaces such that, well, we have F of the bracket, it preserves the bracket. It's just F of A, F of B. And this is for every A and B in G1. An isomorphism of Lie algebras is whenever this F is an isomorphism of vector spaces. Is such an F which is inverted. So now we can start doing the usual constructions in algebra to produce more Lie algebras. Let's see. Let's add a little bit more of a notation. So let's say you have two sets. Say you have S1 and S2 are just sets inside of a Lie algebra. So these are just subsets. Denote the set S1, S2. This is just a set. It's inside of G. And it's a set of all possible brackets of S1 with S2 such that little S1 is in S1 and S2 is in S2. So definition, a subspace say M inside of G, is an ideal well, if you take the bracket of any guy in M and any guy in G, and this guy is inside of M again. So in particular, in an abelian Lie algebra, any subspace is an ideal. I mean, just in the case of groups and so forth, I mean, in the case of algebras, why this definition? Well, whenever you have an ideal, then the quotient space, G mod M, is naturally a Lie algebra. So what is the structure? Well, the obvious one. So what is the structure such a thing? Well, in this quotient space, the elements are A plus M and B plus M. A and B are just any representative. And define the bracket of these two guys to be the bracket of AB plus M. And check that this is a well-defined bracket. I mean, the fact that this is a well-defined map is clear, but you have to check that it satisfies that. Okay, so what this and the fact that we have morphisms, now we can just say the usual stuff, and whenever we have a category and whenever you have the usual sort of lemmas for morphisms, I'll just mention two of them that are kind of really trivial. So if F from G1 into G2 is a morphism of the algebra, then, well, two more useful ones are this. The kernel of F. How is it in Portuguese? Is it núcleo? Núcleo también? Spanish and Portuguese are the same thing. Okay, so the kernel of F is an ideal. Of G1. The image of F is a subalgebra of G2. I guess I can mention that the image of F is isomorphic to G1 modulo the kernel of F. So let's prove a couple of them, and at the same time, let's define what a subalgebra is. Oh, we are going fast. All right, so I want to check that the kernel of F is an ideal of G1. What is the kernel of F? Well, the kernel of F is by definition the set of all A's in G1 such that F of A is equal to 0. So let's take an A inside of the kernel of F. Let's just take any B in G1. And let's compute how much is F of the bracket of A and B. I want this guy to be 0 because I want the bracket of A and B to be again in the kernel. So I want this guy to be 0. But this is, since F is a morphism, this is the bracket of F of A with F of B. A is in the kernel of F, so this is the bracket of 0 with F of B. And the bracket is bilinear, so this is 0. All right, so the image of F is a subalgebra. Well, what does it mean to be a subalgebra? I'll just define what a subalgebra is. The rest of the proof is kind of trivial. Definition. A subspace M inside of G such that MM is again in M is called a subalgebra. In particular, every ideal is a subalgebra. And of course, you have the linear embedding. The embedding of M into G. This is a morphism of Lie algebras. This is a one-to-one morphism of Lie algebras. So M by itself is a Lie algebra. Okay, so why the image of F is a subalgebra of G2? I guess the usual thing. So let's say we have two guys in the image of A. So we have, say, A and B are both in the image of F. Being in the image means that there are some preimages. So there exists, so this is inside of G2, there exists A prime, B prime in G1 such that F of A prime is equal to A, F of B prime is equal to B. And now I want to check that the bracket of A and B is inside of the image of F. Well, this is the bracket of F of A prime with F of B prime, which, since F is a morphism, this is F of the bracket of A prime with B prime. In particular, this is a preimage for the bracket. So that means that the image is closed under the bracket. And the fact that the image of a linear map is a subspace of the target, well, this should know by linear algebra. So this shows this. This is just a trivial fact. I'll let you, this one for you. Okay, so now we know what morphisms are, and now it's easy to produce more algebras. Let's start with one last example on how to produce Lie algebras. This is a way that will give us a lot of Lie algebras. So proposition. Let A be an associative algebra. So if we have any associative algebra, then A itself is a Lie algebra as well. So since we're going to have two different products, let's just denote this product with a dot. Then, as a vector space, I'll take A, but as a bracket, I'll define, could be, take the product in A, take the commutator like this. So then this is a Lie algebra. Well, we have a vector space, it's A itself. The fact skew commutativity is obvious. A times A minus A times A is 0. And the Jacobi identity is just straightforward. Let's check it. So the Jacobi identity goes, let's see. So we want to check that the bracket of A with B and C is the same thing as the bracket of A and B, C, plus the bracket of B with AC. So let's expand everything. So this is if and only if the bracket of A with, let's write down what the bracket of B and C is. So this is BC minus CB. And this is equal to, let's expand this guy, AB minus BA with C. And here we expand this one, B with AC minus CA. So this is an if and only if the bracket of A with BC, well, by definition, this is A times BC minus BC times A. I'm being careful, I'm writing the parentheses. My algebra was associative, so I don't need to. But actually, this theorem is much more general. It works for non-associative algebras as well. But anyhow, so this is the bracket of this with this, minus the bracket of A with CB. So this is minus A, CB plus CB times A. Let's go to the other side of the equal. The bracket of AB with C. AB, C, minus C, AB. Let's see if we can start canceling some things. So we can use associativity here. This is equal to this, and here I am using associativity. So these two cancel. Nothing else. So let's move on. So we have now this, minus BA bracket with C. So we have minus BA C plus CBA. So we can cancel something more. So we have CBA with this. And again, I need to use associativity to cancel this too. Nothing else. So we have plus B with AC minus AC with B. And now we can cancel these two. Again by associativity. And nothing else. And finally, we have minus B with CA. So this is minus B, CA, plus CA, B. Let's see what we're left. So minus BCA, these two get cancelled, and minus BAC plus BAC, this gets cancelled with this, and now why am I having, and this gets cancelled with this. So this is if and only if 0 is equal to 0. So we're fine. Now, actually this is a very well-known statement, and every student, every undergrad knows this. But what's not really well known is that this statement is true even when A is non-associative. So if A is quasi-associative, and even less, and I think this is an exercise for you in the homework, but remark, this is true if A is quasi-associative. That means that the associator is symmetric. So the associator in an algebra is the difference between ABC and ABC. And an algebra is called associative if the associator is 0, and it's called quasi-associative if the associator is symmetric in A and B. Namely, if you just replace A and B, if you switch A and B with B, you get the same expression. So if this is the same as BAC minus BAC. That's an example of what a quasi-associative algebra is. And with this identity, this Jacobi identity is still true. We won't need this at all. Okay, but now, given that proposition, we can construct a lot of Lie algebras. Whenever you have an associative algebra, you have one. In particular, we can construct the most important one to us, which is graph a vector space. We have an associative algebra of endomorphisms of that vector space with composition as the product. So in particular, we get a Lie algebra by the same construction there. So that the associated Lie algebra this Lie algebra is called the general linear Lie algebra, and I use a different name. Instead of using endomorphism of E, since I'm going to have a different product in this Lie algebra, I'll forget about the composition itself. This algebra only has one product, which is the bracket. It's GLV. In the particular case where V is just your field to some power n, then the algebra of endomorphisms of V with composition, well, this is the same thing as the algebra of n by n matrices with coefficients in your field with the product of matrices as the product, as the associative product. The associated Lie algebra is usually denoted GLN. Or if you want to be careful, it's GLN of the corresponding field. And it consists of all possible n by n matrices with coefficients in K. Okay, so now we have one extra example of Lie algebras. Let me mention a couple more, and then we'll stop for a while. So let's do some form of classification. I mean, let me make a trivial remark. A one-dimensional Lie algebra is abelian. And this is obvious because it's a one-dimensional space. It has one generator. By skew symmetry, the product with itself has to be 0. But now, the one-dimensional Lie algebra, therefore, is just isomorphic to the ground field, and the bracket is 0. how can I find an endomorphism? So a morphism from G from any Lie algebra G to this Lie algebra well, let's just repeat what the definition of a morphism was. This is a map from G to K, so that means it's an element of the dual space to G. This by definition is the set of homomorphisms over the ground from G into K, such that, so it's a linear guide there, such that FAB should be the bracket of FA with the bracket of FB. But this bracket is happening in an abelian Lie algebra, so this should be 0. Another way of writing this is for every A and B. Another way of writing this is such a morphism is a linear functional such that F restricted to this space, the space of all possible brackets, is 0. These morphisms are called characters of G. And in general, are not trivial to construct. So before I say the next, let me mention something about this space. This guy, it's an ideal of G. So this is an aside. This space, it's clearly a subspace in G. I mean, the fact that this condition is linear is obvious. But this is also an ideal. And why? Well, this is the obvious thing. Let's grab A in GG and B in G. And by definition, the bracket of A and B, well, is in GG. So it is an ideal. It's called the derived algebra of G. I mean, since it's an ideal, it's a Lie algebra itself. All right, so let's construct one character that we know exists. Again, because so lemma, the trace is a linear map from GLV into K is a character. Proof. The trace of AB minus BA, which is the bracket in GLV, well, this is linear, so this is the trace of AB minus the trace of BA, and this certainly is 0. So this tells us something that a priori might not be completely obvious, but it's that the kernel of the trace is an ideal inside of GLV. In particular, it's a subalgebra. So we have another example of a Lie algebra. The set, so let's call it SLN, is the set of all n by n matrices with entries in our field such that the trace of A is equal to 0. Of course, SLV, you can just do it the same way. I should have done this. There's no obvious way of writing this. Let's do it from Kn to K. All right, so that's a new example of a Lie algebra. So in particular, this guy is an ideal inside of GL. It's not only a subalgebra, but it's an ideal inside of GL. Okay, let me define another series of examples and then we'll finish. So now let B be a bilinear form. So let's do it from a vector space V, tensor V, into K. Be a bilinear form. It doesn't need to be symmetric. It doesn't need to be non-degenerate. There's no condition to it. It's just a bilinear map. All right. So definition of, let's call it O, B, and V, because this depends also on the vector space, is the following. It consists of all endomorphisms. So these are all A inside of endomorphisms of V, or if you want, inside of GLV, such that these endomorphisms preserve in some way this bilinear form. So what is the notion of preserving? It's the following. It's that B of A, V, W plus B of V, A, W is equal to 0 for every V and W. So this gives a lot of Lie algebras, because now we have a Lie algebra lemma. I'm claiming things to say. O, B, V is a Lie algebra. And this gives a lot of Lie algebras. Now, whenever we have a vector space and a bilinear form, we have a Lie algebra. It's called the orthogonal Lie algebra. Well, let's put names later. But let's check there is a Lie algebra and let's stop. The fact there is a subspace inside of GLV, that'll leave to you. It's kind of obvious that this condition is linear. B is a linear operator. But the fact that the bracket is preserved, well, let's check that. Let's take, oops, I chose bad name for A. Well, let's take two matrices A and C. Can't use B there. Acting on V. By definition, the bracket of two guys in GLV, this is AC minus CA acting on V, W. This is, well, B of, since A preserves this guy, so this is the same thing as having minus, well, let's use linearity first. So this is B of AC V W minus B of CA V W. And now let's move this A to this side by using the fact that A is inside of this algebra. So this is minus B of CV AW. Same thing here. This is plus B of AV CW. Let's move this to the other side again. This is plus B of V with CAW minus B of V with ACW. And now this is the bracket of C with A. So this is B of V with the bracket of C with A on W, which is minus the bracket of A and C, which is what I wanted to prove. All right, so now we have a lot of examples. I know this is... Let's take a break for 10 minutes. It's extremely boring now. It's just producing examples, but in a few weeks we'll be proving interesting theorems. Let's stop for a while.